Hi!
Hi.
Welcome to Team 33's final presentation. I'm Kimberly Kerr, and I'm here with my teammates Jack Decker, Crystal L. Ashkar, Noah Hilbig, Gina Schmidt, and Joseph Cabrosi. Today we will be presenting an in-depth analysis of the Mainstays 4-slice toaster oven. The Mainstays 4-slice toaster oven is a popular, convenient miniature kitchen appliance utilized in heating up food with an estimated production volume of 50,000 to 75,000 units annually, as determined via market research. This simple appliance is used in the day-to-day lives of people across the world, whether it be within a corporate kitchenette, college dorm, or within a family's kitchen, as it is both an affordable and convenient option. For our purposes, we will be defining our primary customers as households and our secondary customers as corporations.
This is our fast diagram for our functional analysis that describes the tasks that the toaster oven performs. Our main functive branch is related to food preparation, which is the toaster oven's main objective.
The functional component mapping matrix ensures product requirements are met and can identify opportunities for optimization. If we flip to the next slide, we can see an example where two parts could be combined, that being the metal handle and the plastic handle. We can combine these parts to make our design more efficient.
Here we have our product family design. We have the FDT chart on the left, which shows functionalities that are similar to customer groups, different between the customer groups. And on the right, we have the CCT, which shows the platforms and modules with the corresponding parts. If we go to the next slide, we can see the CAD for primary and secondary and their common interfaces. On the left, we have the household use, which is just the standard use as it already was. And on the right, we have two adjustments for corporate use. We have two slots on each side that are added for another tray. And we've also changed the door material to be stainless steel instead of glass to create more efficient heating.
Shown here is our PFED that highlights our assembly sequence, and we are able to use delayed differentiation to combine our steps until we reach the inner case in our modified assembly sequence. Now we will talk about our design for assembly. Shown here is the calculated total manual assembly time for all of our parts. As you can see, the heating element guard and the foot stopper are good candidates for redesign as they take up a large portion of time. Currently, we have an assembly efficiency of 20.78%. Looking at our FCMM chart and this quad chart, we can further see that the heating element guard, the foot, and the foot stopper are good parts to redesign for manual assembly.
Here's the proposed solution for redesigning the heating element guard to improve manual assembly time. The images on the left show the current heating element guard on the top and bottom of the toaster. In order to target DFAs 1, 5, and 10, we have our solution on the right. The top and bottom guards will be the same, as well as adding an angled notch, which is how the guard is attached to the toaster, as opposed to a 90-degree angled one, to make for easy installation. We estimate this will save about 12 seconds per each assembly. The next slide you can see, we similarly combine parts of the foot to one part that will make for easy insertion by making it a snap fit into the existing toaster design. Subsequently, we estimate that this will reduce assembly time by about 45 seconds.
In considering the possibility of implementing automated assembly, we analyzed the cost of automated assembly within one of our key subsystems, the door subassembly. We first calculated the total cost for automated assembly for each part within the subassembly. Then we considered the handle, metal, plastic, and plate as our platforms for redesign and the door glass as our module for redesign, as all components are lightweight. Visualizing the components I just mentioned within the quad chart, we see that for the platforms, the handle metal and handle plate are of high functional importance as they are used to close the oven and are relatively cheap to manufacture, whereas the handle plastic is both cheap to manufacture and not key to the function of the oven as it only serves an aesthetic purpose. For our module, the door glass is particularly important in function as it helps to enclose the oven, and additionally, it is also relatively expensive to manufacture. One simple redesign for assembly we considered is the combination of the handle plastic and metal into just one handle piece made of plastic, as plastic will be cheaper and easier to manufacture. This redesign follows DFA Rule 1 by reducing the part count from 2 to 1, DFA Rule 2 by reducing fasteners through eliminating the need for fastening the handle metal to the plastic, and DFA Rule 6 by increasing part symmetry through eliminating the handle metal and making the entire handle look the same both from the top and bottom. As a result, from our redesign, the function of the handle is still met in the same manner, and the manufacturing cost decreases by approximately $16.56. We then continue to redesign the manner in which the handle is attached to the door glass. Prior to redesign, 2 screws are used within the handle plate to screw into the handle. These screw holes are hard to access, and the handle plate serves no other purpose than to aid in attaching the handle to the glass. We decided to completely forgo the implementation of the handle plate and instead implement some oversized holes and slightly longer screws already being used elsewhere within the oven to screw the handle to the glass. In doing so, we considered DFA Rule 1 by reducing the part count through eliminating the handle plate, and DFA Rule 7 by adding holes to the door glass to indicate which side of the glass faces upwards, and DFA Rule 13 by implementing oblong holes on the door glass, allowing for adjustment when attaching the handle. As a result, from our redesign, the function of the handle and door glass is still met in the same manner, and the manufacturing cost decreases by approximately $10.56. Here we show an overall change within the subsystem as a result of our redesign for assembly. We see that the handle is now one piece instead of two, and the handle plate has been completely eliminated, and the handle now attaches directly to the door glass via oblong holes.
We will now discuss the process selection for our two redesigned parts. First, looking at the heating element guard, the critical dimensions are the length and thickness of the part, since it must be large enough to support a large mass as detailed in the function component mapping matrix. Additionally, our tolerance is plus minus 0.5 millimeters, as this allows for effective assembly and proper load distribution. The two possible candidate processes for the heating element guard are sheet metal working and machining. Ultimately, we chose sheet metal working as it is much more efficient and cost-effective for the large batch size we intend on producing. Our next redesigned part is the foot assembly, which includes the foot and the foot stopper. The most critical dimensions are shown and include the thickness, length, and draft angle of the foot, since it has to support a large mass and volume, as detailed in the function component mapping matrix. Specifically, the thickness and draft angle will allow for extra support at the base of the toaster oven. Additionally, the dimension of the snap rivet is critical, as it must be able to fit in with other components. The critical tolerance is plus minus 0.1 millimeters, as the top portion of the foot is very intricate and requires a smaller tolerance to maintain performance.
The two possible process candidates for the foot include injection molding and compression molding. Ultimately, injection molding was chosen because it is better suited in producing parts with intricate details and is generally a quicker process than compression molding.
Moving into design for manufacturing, we first analyzed the cost of manufacturing the heating element guard with sheet metal manufacturing before analyzing the design with DfM Pro. This cost includes material cost, operating costs, and total die costs, and it came to $5.11. After analyzing with DfM Pro, we found no errors in this design, so it actually stayed the same at $5.11. We also analyzed the manufacturing costs using hubs.com and extrapolated that data up to 100,000 parts, and this came in at $2.29. Our analytical methods came in at over 2 times as costly as the Hubs quote, but both feature no changes before and after the DfM Pro analysis. Next, we analyzed the cost of manufacturing the foot assembly with injection molding before analyzing the design with DfM Pro. Again, this cost includes material, operating, and total mold costs, and it came out to 85.27 cents per part.
Utilizing DfM Pro, we checked for any possible areas of concern for the manufacturing process. DfM Pro gave us 4 errors to address. 3 of these errors related to the complex geometry within the snap fit attachment located at the top of the foot, and 1 error related to the non-uniform thickness that existed as a result of the foot having a hollow design. To address the errors relating to the snap fit attachment, we completely removed the complex geometry within the snap fit nub. Then, following DFIM 4, we added 0.2 millimeter fillets to all edges along the snap fit nub. Then, to address the non-uniform wall thickness within the base of the foot, following DFIM 3, we implemented a 5-degree draft angle both inside and outside the base of the foot. And then following DFIM 2, we added cuts to the base of the snap fit nub. After implementing these changes, we can see the updated CAD model of the foot on the right.
As you can see, the foot redesigned after DfM Pro comes out to be about 10 cents less at $76.17. The product's function stays the same, and we're aiming to decrease both manufacturing and assembly costs. Now we're going to talk about the product service system. The product offers both improvements to the customer experience and reducing the negative impacts on the environment. We will provide bulk discounts to company purchasing, offer integrated data collection for the owner to collect user data over time, encourage shared use within 2 trays within companies to reduce energy. We'll use recyclable materials and provide end-of-life recycling. Now our conclusions and design critiques. As you can see, the benefits, the DFA manual reduces 12.3 seconds for the heating element guard and 43.9 seconds for the foot. For DFA, we aim to save $27.12. DFM, we have no improvements. And for the heating element guard and for the foot, we aim to save about 9 cents per part. And the total cost reduction will be about $27.21. 2 drawbacks is that we will need intercase hole adjustments to assist the heating guard alignment. And the product life of the foot may be reduced to cheaper material. If we started over, we would take greater care with the fast diagram and ultimately determine where the project goes.